What if I told you the universe keeps a memory, an echo from the very dawn of time, a whisper older than stars, older than galaxies? It's not science fiction. It's real, and it's all around us, hidden in plain sight. Picture this: every time you tune an old television to static, a tiny fraction of that snow isn't just random noise. It's the universe's first light, stretched and faded across billions of years, but still reaching us, a cosmic fingerprint from when everything began. This isn't just background radiation. This is the afterglow of creation itself. We're talking about the cosmic microwave background, or CMB, the oldest light in existence. It's the relic of a time when the universe was a seething, newborn sea of energy, just 380,000 years after the Big Bang. Back then, space wasn't black. It glowed like the surface of the sun, a blinding fog of particles and light. And though that light has traveled for over 13 billion years, cooling and dimming into microwaves, it still holds secrets about how galaxies formed, how the cosmos grew structure, even clues about the very fabric of reality. This is the ultimate cold case file, written in photons, but here's what's truly mind-blowing: we can read it. Scientists have mapped this ancient light with satellites like Planck and WMAP, revealing tiny fluctuations, ripples in the cosmic pond that became the galaxies and voids we see today. And in this video, we're diving deep into 30 astonishing facts about the CMB, from how it proves the Big Bang to why it might hint at parallel universes. You'll discover how this light carries echoes of quantum fluctuations from the universe's first trillionth of a second, how it's still shaping our understanding of dark energy, and why it's the closest thing we have to a time machine. So buckle up, we're about to trace the universe's oldest light back to its origins and uncover the stories it's been waiting to tell us since the beginning of everything. Think of the cosmic microwave background as the universe's very first selfie, a snapshot taken when everything we know was just an infant, barely 380,000 years old. At that moment, the cosmos was nothing like what we see today. It was a dense, scorching plasma, so hot that atoms couldn't even form. Electrons and protons raced around freely, scattering light in all directions like a thick, glowing fog. But then, something extraordinary happened. As the universe expanded, it cooled just enough for electrons and protons to finally link up, creating neutral hydrogen atoms. Suddenly, light could travel uninterrupted for the first time. That flash of liberation, the moment the fog lifted, is what we now detect as the CMB. This ancient glow isn't just a relic, it's a time capsule. The temperature of that light, now cooled to just 2.7 degrees above absolute zero, tells us exactly how much the universe has stretched over billions of years. The tiny fluctuations in its brightness, those are the seeds of everything, the faint blueprints for galaxies, stars, and even the voids between them. It's like finding the scribbled sketches of a master artist, revealing how the cosmos went from a smooth, simmering soup to the intricate web of structures we see today. What's breathtaking is how precisely this fossilized light matches our predictions. Scientists calculated decades ago that if the Big Bang really happened, the universe should be bathed in a faint microwave whisper. And when researchers Penzias and Wilson stumbled upon it in 1965, thanks to mysterious static in a radio telescope, it was the smoking gun that confirmed our cosmic origin story. The CMB doesn't just hint at the Big Bang, it is the Big Bang's afterparty, still echoing through space, and every time we study it, we're deciphering the universe's earliest diary entry. Sometimes the greatest discoveries aren't made by those searching for them, but by those simply paying attention to the noise. In 1964, two radio astronomers at Bell Labs, Penzias and Wilson, were wrestling with a stubborn problem. Their massive Holmdel-Horn antenna, built to study radio waves from space, kept picking up a mysterious hiss, No matter where they pointed it, no matter how meticulously they cleaned the instrument, even scraping away pigeon droppings, that annoying static wouldn't vanish. It was faint, uniform, and utterly inescapable, like the hum of a refrigerator that never turns off. What they didn't realize, they'd just bumped into the oldest sound in the universe. This wasn't just technical interference. That persistent noise matched a prediction few people even knew about. Years earlier, physicists like Robert Dicke had theorized that if the Big Bang really happened, the entire universe should be bathed in a faint glow of microwaves, the cooled remnants of its fiery birth. But no one had found it. Penzias and Wilson, unaware of this theory at first, had accidentally tuned into the echo of creation itself. When they connected with Dicke's team at Princeton, the revelation hit like lightning. That noise was the cosmic microwave background, the afterglow of the universe's infancy. The irony is delicious. A discovery that reshaped our understanding of cosmic origins began with two frustrated engineers chasing down what they thought was a faulty antenna. Their persistence turned a nuisance into a Nobel Prize-winning breakthrough. In 1978, Penzias and Wilson stood on that prestigious stage, honored for uncovering what's now called the smoking gun of the Big Bang. But here's the kicker: their antenna wasn't even designed for cosmology. It was built for satellite communication. The universe whispered its oldest secret through a machine meant for phone calls, proving once again that science often finds its greatest truths in the unlikeliest places. What makes their story so compelling isn't just the serendipity, it's how perfectly the CMB matched the Big Bang's predictions. That faint hiss was precisely the temperature theorists expected, around 3 degrees above absolute zero, stretched by the expansion of the universe over billions of years. Penzias and Wilson didn't just stumble upon random noise, they found the final piece of a puzzle physicists had been assembling for decades. And in that static, they gave us something extraordinary, direct evidence that our cosmos had a beginning, a moment when everything, time, space, matter, leapt into existence. Their accident became the cornerstone of modern cosmology, but imagine if they'd shrugged it off. What if they'd assumed the noise was just a glitch and moved on? Science is filled with near misses, moments when curiosity triumphed over convenience. That's the real lesson here. Sometimes the universe hides its deepest truths in the details we're tempted to ignore. The next time you hear static on the radio between stations, remember, you're listening to the same ancient murmur that rewrote history. It's not just noise. It's the sound of the universe introducing itself. There's something eerily perfect about the cosmic microwave background, something that makes physicists both marvel and double-check their instruments. When we analyze its light, we find a spectrum that's almost too pristine, too precise. It matches what scientists call a blackbody curve with staggering accuracy, like a fingerprint that hasn't smudged over 13 billion years. A blackbody is a theoretical object that absorbs all radiation hitting it and re-emits it with a distinctive pattern, one that depends only on temperature, not composition. Stars are close to blackbodies, but none are as flawless as the CMB. The CMB's temperature, 2.725 Kelvin, just a whisper above absolute zero. That number might seem arbitrary, but it's one of the most precisely measured figures in all of cosmology, accurate to within 1,000th of a degree. And here's why that's extraordinary. This near-perfect blackbody spectrum is exactly what the Big Bang predicts. When the universe was young and opaque, its dense plasma constantly absorbed and re-emitted radiation, creating thermal equilibrium, a state where energy distributes evenly. As the cosmos expanded and cooled, that equilibrium froze into the light we now detect. The CMB spectrum is essentially a fossilized moment of that ancient thermal harmony, undisturbed by intervening cosmic events. This perfection isn't just a curiosity, it's a cornerstone of modern cosmology. Alternative theories like the steady-state model, which suggested the universe had no beginning, struggle to explain such a precise blackbody. Only the Big Bang's rapid expansion and cooling can produce this signature. Satellites like COBE, launched in 1989, confirmed the CMB's blackbody nature with such precision that the data points practically lie on top of the theoretical curve. The graph is so exact it's almost unsettling, like finding a Renaissance painting where every brushstroke aligns with a mathematical formula. Yet even in this near perfection, there are tiny, telling imperfections. The CMB's temperature isn't uniform across the sky. It varies by minuscule fractions of a degree. These fluctuations are the universe's way of whispering its secrets. They reveal where matter was slightly denser in the early cosmos, regions that would later collapse under gravity to form galaxies and galaxy clusters. But the overall blackbody curve, that's the universe's way of signing its work, a seal of authenticity on the Big Bang's legacy. When you look at that curve, you're seeing the afterglow of a time when the entire cosmos was in perfect thermal sync, a harmony preserved in microwaves, a lullaby from the dawn of everything. Before the universe became transparent, it was a cosmic hall of mirrors, a seething, opaque fog where light couldn't travel more than a fraction of an inch before being swallowed by free electrons. But 380,000 years after the Big Bang, everything changed. The cosmos had finally cooled enough, down to about 3000 Kelvin, for one of the most important handshakes in history. Protons and electrons, after an eons-long game of chase, finally linked up to form neutral hydrogen atoms. This cosmic truce, known as recombination, wasn't just a chemical shift. It was the moment the universe flipped the lights on for the first time. Think of it like a dense morning fog suddenly clearing. Before recombination, light was trapped, bouncing endlessly between particles in a plasma so thick you couldn't see your hand in front of your face, if you had a hand or a face or even eyes yet. But once those electrons settled into orbit around protons, the fog lifted. Photons, no longer scattered by free electrons, could finally stream freely across space. That first burst of liberated light is what we now detect as the cosmic microwave background, the afterglow of the universe's first dawn. What's astonishing is how sudden this transition was. Cosmologists estimate the universe went from opaque to transparent in just a few thousand years, a blink in cosmic terms. And here's the wild part: those photons released during recombination have been traveling undisturbed ever since. The CMB we observe today is made of the same light that first pierced the cosmic fog, now stretched by the expansion of the universe from visible wavelengths into microwaves. When you look at a CMB map, you're not just seeing a snapshot of the early universe, you're seeing the actual photons that witnessed atoms forming for the first time. But why was this moment so special? Because it froze the universe's baby picture. Before recombination, matter and radiation were locked in a violent dance, constantly pushing and pulling each other. The moment atoms formed, that tug-of-war ended, and the photons decoupled from matter, preserving a pristine imprint of the universe's conditions at that instant. The tiny temperature variations in the CMB, those are essentially sound waves frozen in time, the echoes of density fluctuations that would later grow into galaxies. This transition didn't just make light visible, it made the universe navigable. For the first time, structures could form without being constantly blasted apart by radiation pressure. Gravity finally had a chance to work its magic, pulling matter into the seeds of galaxies. In a way, recombination wasn't just the universe's first light show, it was the starting gun for cosmic construction. And every time we study the CMB, we're reading the blueprint of that construction project, written in the oldest light there is. One final twist: we owe our existence to this moment. If recombination had happened slightly earlier or later, the delicate balance of matter and energy might have prevented galaxies, and eventually stars, planets, and us from forming at all. The CMB isn't just a relic, it's proof that the universe got its recipe just right, leaving behind a glow we can still decode 13 billion years later. Those microwaves aren't just ancient radiation, they're the universe's first breath still exhaling across the cosmos. At first glance, the cosmic microwave background seems almost boring, a uniform sea of microwaves like an endless, featureless fog. But look closer and you'll find it's anything but smooth. The CMB is speckled with microscopic temperature fluctuations, variations as subtle as 1 part in 100,000. To put that in perspective, imagine a 1,000,000-watt light bulb glowing with a brightness that wobbles by just 10 watts. These tiny imperfections might seem insignificant, but they're the most important fingerprints in the cosmos. They're the seeds of everything, the blueprints for galaxies, galaxy clusters, and the vast cosmic web we see today. These fluctuations weren't random noise. They were imprinted in the universe's earliest moments, born from quantum jitters so small you'd need a microscope to see them, if microscopes could peer back in time. In the first trillionth of a second after the Big Bang, quantum mechanics caused space itself to writhe with tiny density variations. As the universe expanded, those microscopic wrinkles were stretched to cosmic scales, frozen into the fabric of space-time. By the time recombination happened, they'd grown just enough to leave faint imprints in the CMB's temperature. Warmer spots, slightly denser regions where matter had begun clumping together. Cooler spots, emptier patches where gravity had less to work with. This discovery didn't come easily. When NASA COBE satellite first mapped these fluctuations in 1992, scientists were stunned by how perfectly they matched predictions. The variations were so minuscule that lead researcher George Smoot famously compared finding them to spotting the ripples from a pebble dropped in a choppy ocean. But those ripples told an epic story. They showed exactly how matter was distributed when the universe was only 380,000 years old, like a snapshot of a construction site before the first bricks were laid. Later missions like Planck and WMAP sharpened the image. Planck's maps, released in 2013, revealed these temperature differences with precision down to millionths of a degree. The patterns weren't random, they followed a precise mathematical rhythm like notes in a cosmic symphony. Scientists call this the power spectrum, and it's packed with clues. The spacing of those peaks and valleys reveals the universe's composition, how much is ordinary matter, how much is dark matter, even how fast space is expanding. It's as if the universe left us a coded message in the CMB's temperature bumps, and we're finally learning to read it. What's astonishing is how much these tiny variations mattered. Over billions of years, gravity amplified them, pulling denser regions together into galaxies and leaving emptier zones to become cosmic voids. Without those initial imperfections, the universe would have stayed a featureless soup. No stars, no planets, no us. The CMB's temperature map is essentially a family photo of the cosmos before it grew up, a grainy ultrasound of the infant universe, showing the first hints of the structure that would define everything to come. And here's the kicker: these fluctuations might hold answers to even bigger mysteries. Some of the patterns don't quite match our models, hinting at physics we don't yet understand, perhaps evidence of other universes brushing against ours in the first moments of time. Others suggest the universe's expansion isn't perfectly even, nudged by forces like dark energy. The CMB isn't just a relic, it's a Rosetta Stone waiting to be fully deciphered. Every time we study those tiny temperature ripples, we're not just looking back, we're uncovering the rules that shaped reality itself. Here's something that bends the mind. The light we now call the cosmic microwave background didn't always look like this. When it first burst free during recombination, it was blinding, a searing white-hot glow brighter than the surface of the sun. So how did it become the faint microwave whisper we detect today? The answer lies in one of the universe's most relentless forces, expansion. Over 13 billion years, the very fabric of space stretched, and with it, the light traveling through that space got dragged along for the ride. Picture throwing a pebble into a pond. The ripples start close together, but as they spread outward, they stretch apart. Light behaves the same way. Those original photons from the early universe began with short, energetic wavelengths, what we'd perceive as visible light, maybe even yellowish-white like sunlight. But as space expanded, the waves got pulled longer and longer, like taffy stretched to its limit. By the time this light reached us, its wavelengths had been redshifted so dramatically that they'd shifted entirely out of the visible spectrum, sliding through infrared and stopping in the microwave range. We're talking about a redshift factor of around 1,000, meaning the light waves we see today are about 1,000 times longer than when they were first emitted. This extreme redshift is why we can't see the CMB with our eyes. Our visual range caps out at wavelengths around 700 nanometers, but the CMB's waves now measure millimeters long. To put that in perspective, if those original photons were the size of a grain of sand, today they'd be as long as a car. That's how much the universe has stretched them. And here's the wild part. This stretching didn't just affect the light's wavelength, it also sapped its energy. The CMB's photons, once blisteringly hot, now carry barely a whisper of warmth, cooled to just 2.7 degrees above absolute zero. But redshift isn't just a curiosity, it's a measuring stick for cosmic history. The amount of stretching tells us exactly how much the universe has expanded since recombination. It's like finding an ancient rubber band and seeing how far it's been pulled. This single number, that redshift factor of 1,000, helps physicists calculate the age of the universe, the rate of its expansion, even the way dark energy has influenced its growth. Without redshift, the CMB would just be an ancient glow. With it, it becomes a time machine, letting us peer back to the universe's first moments with startling precision. The fact that we can detect this stretched light at all is a testament to human ingenuity. Early attempts to find the CMB used radio telescopes, but it wasn't until satellites like CMB and Planck that we mapped it in detail, teasing out its subtle variations. These missions didn't just confirm the Big Bang, they gave us a front-row seat to the universe's most dramatic stretch, a transformation so vast it turned fire into frost. Every time we study the CMB, we're not just observing light. We're witnessing the echo of a universe that's been running, expanding, and evolving for nearly 14 billion years. And the photons telling that story have been on that journey every step of the way, stretched but never broken. The cosmic microwave background isn't just a distant glow. It's the wallpaper of the universe, enveloping us in every direction. No matter where you point a microwave antenna, whether toward the bustling plain of the Milky Way or the emptiness of intergalactic space, that faint hiss of ancient light is there. It's not coming from a single source, but from everywhere at once, a ghostly reminder that we're standing inside the aftermath of the Big Bang. Imagine stepping into a room where every surface, every corner, even the air itself hums with the same faded light. That's the CMB. This omnipresence isn't just poetic, it's a critical clue about the shape of reality. The near uniformity of the CMB tells us the early universe was remarkably smooth, with matter distributed almost evenly across space. Those tiny temperature wrinkles we've talked about, they're like barely visible brushstrokes on an otherwise blank canvas, hints of structure emerging from the formless. But here's what's wild, the way those wrinkles are spaced across the sky isn't random. Their patterns act as a cosmic yardstick, revealing whether the universe is flat, curved like a saddle, or wrapped like a sphere. Think of it like trying to measure the Earth's shape by studying shadows. If light angles match predictions on a flat surface, you're on a plane. If they're distorted, you're on a curve. The CMB does something similar for the cosmos. By analyzing the apparent size of those temperature fluctuations, scientists can calculate the universe's geometry. And the verdict, within razor-thin margins, the data says flat. Not flat like a sheet of paper, but flat in the sense that parallel lines stay parallel forever, and the angles of a triangle add up to 180 degrees, just like the geometry we learned in school. But flatness isn't just about angles, it's a window into the universe's composition. A flat geometry implies a precise balance between matter, energy, and the expansion rate, a Goldilocks scenario where everything adds up to critical density. Too much matter and space would curve inward like a ball. Too little and it'd bow outward. The CMB's uniformity suggests we're riding the razor's edge, with dark energy, dark matter, and ordinary matter combining in proportions that keep spacetime astonishingly level. It's as if the universe did the math perfectly, leaving behind a microwave sky that doubles as a solutions manual. Even more intriguing, this all-sky glow behaves like the ultimate control experiment. When astronomers study distant galaxies or supernova, they're often peering through layers of cosmic dust or gas that can distort their view, but the CMB, it's behind everything and equally in front of everything. That means its light has traveled the same distance no matter where we look, giving us a pristine reference frame. By comparing the CMB's uniformity with the lumpy distribution of galaxies today, we can trace how gravity sculpted the cosmos over billions of years. Those subtle wrinkles in the CMB aren't just frozen sound waves, they're the starting coordinates for the universe's entire structural evolution. So the next time you hear about the CMB's uniformity, remember it's not boring. It's the ultimate blank slate, a canvas where the faintest brushstrokes hold the blueprints for everything that followed, and the fact that it fills the entire sky. That's not an accident. It's the universe showing its hand, revealing the geometry, composition, and even the fate of spacetime itself, written in microwaves echoing from every direction at once. Those tiny temperature variations in the cosmic microwave background aren't just fingerprints, they're cosmic hieroglyphs, telling a story of the universe's most violent growth spurt. Scientists call it inflation, a theory that in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, space itself expanded faster than the speed of light, ballooning from smaller than an atom to the size of a grapefruit. That sounds impossible, but here's where the CMB becomes our time machine. Without inflation, those delicate fluctuations in the microwave background wouldn't make sense. The universe would be too lumpy in some places, too smooth in others. Instead, the CMB's patterns match inflation's predictions with eerie precision, like finding a fossil with the exact features your model said it should have. What's breathtaking is how inflation solves cosmic mysteries we didn't even know were connected. Take the horizon problem. The CMB's temperature is nearly identical in opposite sides of the sky regions, so far apart that light wouldn't have had time to travel between them in the universe's age. It's like walking into a bakery where every cupcake, from Tokyo to Toronto, has identical frosting swirls despite no baker coordinating them. Inflation fixes this by suggesting these regions were once neighbors, crammed together before space stretched them apart faster than light could keep up. The CMB's uniformity isn't a coincidence. It's evidence of this ultra-fast stretching, freezing those quantum jitters into cosmic scale patterns. But inflation didn't just smooth things out, it amplified the microscopic into the astronomical. Quantum fluctuations, those tiny ripples in spacetime's fabric, got stretched to planetary scales during inflation. Imagine blowing up a balloon with microscopic dots drawn on it. As it inflates, those dots become continents. That's exactly what happened to those quantum wrinkles. They became the density variations we now see in the CMB, the seeds for galaxies and voids. Satellites like Planck have measured these patterns down to millionths of a degree, and their statistical fingerprints, the way hot and cold spots cluster, match inflation's predictions so perfectly it's almost unnerving. Here's where it gets even wilder. Inflation isn't just a theory about our universe's past, it hints at realities beyond our own. Some models suggest inflation never truly stopped, that our cosmos is just one bubble in an endless froth of universes, each with different physical laws. The CMB might hold clues to this multiverse. Certain anomalies in its polarization patterns, like large-scale, cold spots, could be bruises from collisions with other bubble universes in the cosmic foam. It's speculative, but the fact we can even ask these questions shows how the CMB has become more than a relic. It's a portal to physics at energies we'll never recreate on Earth. The real triumph, inflation, was theorized in the 1980s, decades before we had the instruments to test it. When Cope and later Planck mapped the CMB's fluctuations with precision, they didn't just confirm the Big Bang, they validated a mechanism so abstract it sounded like science fiction. Those microwave patterns are the ultimate cold case evidence, pointing to an event that lasted less time than it takes light to cross a single proton. Yet here we are, reading its aftermath in the sky's faint glow. The CMB doesn't just show us the universe's baby pictures, it captures its first scream, a burst of expansion so violent it set the stage for everything that followed. Hidden in the cosmic microwave background's subtle patterns is one of the most shocking discoveries in modern cosmology, proof that the universe isn't just expanding but accelerating. It sounds impossible. How could the afterglow of the Big Bang reveal something as elusive as dark energy? The answer lies in the CMB's ability to act as a cosmic scale, measuring not just the universe's shape but its fate. When scientists first mapped the CMB's fluctuations, they noticed something peculiar. The spacing between those temperature ripples, the acoustic peaks in the power spectrum, pointed to a universe with near-perfect flat geometry. But flatness comes with a catch. For space-time to be this level, the cosmos must contain exactly enough matter and energy to balance its expansion rate. Problem was, when astronomers added up all the visible stars, gas, and even dark matter, they only accounted for about 30% of what was needed. Something invisible was making up the difference. That's where dark energy entered the picture. Theorized as a repulsive force counteracting gravity, dark energy would explain why the universe wasn't just flat but expanding faster over time. But the CMB didn't just hint at its existence, it helped prove it. By comparing the CMB's snapshot of the early universe with observations of distant supernova, which also showed accelerating expansion, scientists realized dark energy wasn't just real, it dominated the cosmos. That ancient light held the receipts. 70% of the universe's energy budget was this mysterious, space-stretching force. The real magic is in the details. The CMB's acoustic peaks are spaced in a way that only makes sense if dark energy started driving cosmic acceleration relatively recently, around 5 billion years ago. Before that, gravity's pull was winning, slowing the expansion. But as the universe grew more spacious, dark energy's push overcame gravity's grip, like a phantom foot slamming on the gas pedal. The CMB captured the moment this tug-of-war was set up, preserving the conditions that would eventually lead to dark energy's triumph. Here's the kicker: without the CMB, we might have dismissed dark energy as a fluke. Supernova data alone could have been written off as observational error. But when two completely independent lines of evidence, the early universe's blueprint and today's runaway expansion, pointed to the same conclusion, it became undeniable. The CMB didn't just confirm dark energy, it revealed when and how it took over, turning a theoretical placeholder into the defining feature of our cosmos. Those microwaves aren't just relics, they're time-stamped evidence of the universe's greatest plot twist. Think of the cosmic microwave background as the universe's ultimate Polaroid, a faded but flawless snapshot of reality in its toddler years, frozen the moment light broke free. This isn't just a blurry image, it's a high-resolution selfie of the cosmos at 380,000 years old, capturing everything from the density of matter to the echoes of primordial sound waves. Like opening a time capsule buried at the dawn of time, scientists can peel back layers of this microwave glow to uncover secrets about how the universe looked, sounded, and even how it would evolve over billions of years. Take density, for example. The CMB's temperature variations, those faint hot and cold spots, are essentially a cosmic barcode. Warmer regions, they mark where matter was slightly denser, like invisible mountains in the fabric of space. Cooler patches, valleys where matter was sparser, But here's what's astonishing. The precise distribution of these fluctuations tells us exactly how much ordinary matter, dark matter, and even dark energy existed back then. It's as if the early universe stamped its ingredient list into the light, and we're just now learning to read the recipe. Then there's composition. The CMB's light carries spectral fingerprints that reveal the universe's original elements. When you break down its photons, you find traces of hydrogen and helium in ratios that match predictions of Big Bang nucleosynthesis, the process that forged the first atoms. The numbers are uncanny, about 75% hydrogen, 25% helium, and mere traces of lithium. These ratios are like finding a receipt from the universe's first grocery run, confirming what theorists had calculated decades before we could observe it. But the real showstopper, sound, yes, sound. In the early universe's plasma soup, pressure waves rippled through the dense, hot gas, creating oscillations like the vibrations of a colossal bell. When atoms formed and light escaped, those waves froze mid-echo, imprinting their rhythm onto the CMB. Today, we can decode these patterns, called baryon acoustic oscillations, as concentric rings in the temperature maps, like ripples from stones dropped in a pond. The spacing of these rings acts as a cosmic ruler, letting us measure the universe's expansion with precision. It's as if the universe left us a voicemail from its infancy, and we're just now playing it back. What makes this snapshot so invaluable is its purity. Unlike later cosmic structures twisted by gravity and star formation, the CMB is untouched, a pristine record of the universe before it got complicated. Every fluctuation, every spectral line, every acoustic peak is a clue waiting to be deciphered. We're not just looking at a picture, we're holding the universe's birth certificate, its first diary entry, and its blueprints all at once. And the wildest part, this photograph wasn't taken with a lens. It was developed over 13 billion years using space-time itself as the darkroom. The CMB holds a secret symphony, a set of faint echoes from when the universe was so dense it could carry sound. These aren't metaphors, literal pressure waves rippled through the primordial plasma like bass notes through water, and their fossilized imprints are still visible in the microwave background's temperature patterns. Scientists call them baryon acoustic oscillations, and they're essentially the universe's first recording. Here's how it worked. In the first few 100,000 years after the Big Bang, the cosmos was a seething cauldron of particles and radiation. Photons and baryons, protons and neutrons were locked in a violent tug of war. Photons exerted outward pressure while gravity tried to pull matter together. This created regions where plasma compressed and rarefied rhythmically, generating spherical sound waves that expanded at nearly half the speed of light. But when recombination happened and atoms formed, the music stopped abruptly. The photons decoupled, freezing those waves in place mid-oscillation, like a phonograph needle lifted off a spinning record. The result, a cosmic fingerprint. These frozen waves left concentric ripples in matter's distribution, dense shells where baryons piled up at the edges of the sound waves' reach. As the universe expanded, these shells stretched to nearly 500 million light-years across, becoming the preferred spacing for galaxies. Today, when astronomers map millions of galaxies, they find this signature. Galaxies are slightly more likely to be separated by this exact scale than any other distance. It's as if the universe has a hidden grid and the CMB holds its blueprint. What's astonishing is how clearly these patterns show up in CMB maps. Satellite missions like Planck didn't just detect the waves' frozen peaks, they measured their exact scale. The spacing between temperature fluctuations matches predictions down to a 1% margin of error, like finding a prehistoric drumhead still vibrating at the predicted frequency. This isn't just confirmation of sound, it's a Rosetta Stone for cosmic structure. By comparing these ancient oscillations with modern galaxy surveys, we can track how gravity warped their perfect symmetry over billions of years. The real magic lies in what these sound waves reveal. Their size acts as a standard ruler because we know how fast sound traveled in the early plasma. Any apparent stretching or squeezing of their imprints tells us how much the universe has expanded since. It's like finding fossilized footprints where the stride length is known. Measure how compressed they look now, and you can calculate how far the ground has stretched. This technique has become one of cosmology's most precise tools for measuring dark energy's influence, confirming that the universe's expansion is accelerating. But perhaps the wildest implication is this: the same physics that makes a speaker cone vibrate pressure waves moving through a medium once operated on a scale encompassing the entire observable universe. Those baryon acoustic oscillations are the deepest bass notes imaginable, with wavelengths so vast they could wrap around the Milky Way 50 times. And we're not just theorizing about them, we're seeing their shadows in the CMB's subtle glow, a reminder that the universe didn't just unfold in silence. It rang like a bell at its birth, and the echoes never truly faded. They just redshifted into microwaves, waiting for us to listen. Hidden within the cosmic microwave background's gentle glow is a subtle but revolutionary feature: polarization. This isn't just light, it's light with a sense of direction, like sunlight glinting off the surface of a lake. The CMB's photons don't just reach us with a specific temperature, they also carry a whisper of alignment, a faint preference in how their electric fields vibrate. And this polarization isn't random. It's a cosmic breadcrumb trail pointing us toward one of the most elusive phenomena in physics: primordial gravitational waves from inflation. Here's why this matters. When light scatters off particles like electrons in the early universe's plasma, it gets polarized, organized into a specific orientation. The CMB's polarization patterns fall into two categories: E modes, which curl like the petals of a flower, and B modes, which swirl like fingerprints left by gravitational waves. It's those B modes that have cosmologists holding their breath. They're the smoking gun for inflation's violent expansion, a time when space-time itself rippled with waves powerful enough to stretch the fabric of reality. Finding them would confirm that the universe didn't just expand, it exploded into being faster than light itself. The hunt for these B modes has fueled some of cosmology's most daring experiments. Projects like BICEP, nestled in the thin, dry air of Antarctica, and LIGHT-BIRD, a future satellite mission, are designed to detect polarization with sensitivity down to a billionth of a degree. Why go to such extremes? Because inflation's gravitational waves would have left an imprint so faint it's like trying to spot a single snowflake in a blizzard. The signal, if it exists, would be buried in the CMB's noise, drowned out by galactic dust or even the afterglow of the Big Bang itself, but the payoff would be staggering. Detecting primordial B modes wouldn't just prove inflation happened, it would tell us when and how it happened. The strength of these swirls would reveal the energy scale of inflation, whether it occurred at the grand unification of forces or some even more exotic physics. It's like uncovering the signature of the universe's first heartbeat, a pulse so powerful it set everything into motion. And there's another twist. The CMB's polarization doesn't just hint at gravitational waves, it also maps the universe's entire matter distribution. When photons traveled through regions of dense dark matter, their paths were bent slightly, warping the polarization patterns in a way that lets us reconstruct where matter was clumping even before galaxies formed. It's as if the CMB handed us a pair of X-ray glasses, revealing the invisible scaffolding of the cosmos. The challenge: false alarms. In 2014, BICEP-2 initially claimed a detection of B modes, only to later realize galactic dust had muddied the signal. The near miss was a reminder of how delicate this search is, but also how tantalizing. Future missions like LIGHT-BIRD aim to scan multiple frequencies, separating cosmic signals from dust with surgical precision. If they succeed, we won't just be studying the CMB, we'll be eavesdropping on the universe's first moments, hearing the echoes of spacetime's birth cries in the polarization of ancient light. What's breathtaking is how much rides on something so subtle. The difference between a random polarization pattern and one imprinted by gravitational waves could be the difference between confirming our boldest theories or rewriting them entirely. The CMB's light isn't just a relic, it's a cipher encoding the universe's deepest secrets in the quiet alignment of its photons. And with every new experiment, we're one step closer to cracking the code. The cosmic microwave background isn't just ancient, it's slowly fading. It's glow-dimming as the universe stretches into the future. Back when this light first broke free during recombination, it blazed at around 3000 Kelvin, hot enough to glow white-hot like the surface of the sun. Today, it's cooled to a faint whisper just 2.7 degrees above absolute zero. But here's the thing, that temperature isn't static. The CMB is cooling imperceptibly, steadily, as space itself expands. Every billion years, its temperature drops by a fraction of a degree, a silent reminder that even the universe's oldest light isn't immune to time's relentless march. This cooling isn't random, it's physics in its purest form. As the universe expands, the wavelengths of CMB photons stretch along with it, shifting from shorter, energetic waves to longer, cooler ones. It's like a cosmic rubber band being pulled thinner and thinner, its heat dissipating into the void. The math behind this is strikingly elegant. The CMB's temperature is inversely proportional to the universe's scale. Double the size of the cosmos and the CMB's temperature halves. In another 10 billion years, that 2.7 Kelvin glow will have chilled to barely 1 degree above absolute zero. The universe's first light, once blinding, will have faded to a deeper frost. What's fascinating is how this cooling connects to the universe's ultimate fate. If dark energy keeps accelerating expansion, the CMB's temperature will eventually plummet toward absolute zero, its photons stretched into undetectable radio waves. Distant civilizations billions of years from now might peer into the sky and find no trace of the CMB at all. The afterglow of creation, visible to us by sheer cosmic luck, could vanish entirely for observers in the far future. This isn't just a slow fade, it's the erasure of a cornerstone of cosmology, a relic that once proved the Big Bang itself. Yet even as it cools, the CMB holds clues about the universe's past warmth. By measuring its current temperature with exquisite precision down to millionths of a degree, scientists can extrapolate backward, reconstructing the exact moment recombination occurred. Those calculations don't just match theory, they validate the entire thermal history of the cosmos. The CMB's cooling isn't a bug in the system. It's a feature, a built-in cosmic clock ticking in lockstep with spacetime's expansion. Here's a sobering thought. The CMB's temperature is one of the few constants that isn't constant at all. Unlike the speed of light or the charge of an electron, this number changes over time, a living record of the universe's growth. Those microwaves washing over Earth today are colder than the ones that bathed the first galaxies, and warmer than the ones that will greet civilizations of the distant future. In that slow, inevitable cooling, we're witnessing more than just physics. We're watching the universe grow old, one photon at a time. Imagine standing in a quiet snowfall, surrounded by countless tiny flakes drifting silently through the air. No matter which way you turn, the snowflakes keep falling, filling every inch of space around you. That's what the cosmic microwave background is like, except instead of snow, it's an endless sea of microwaves, and instead of a winter sky, it's the entire universe. This ancient glow doesn't just come from distant galaxies or bright stars. It's literally everywhere, even in the darkest, emptiest voids between galaxies where nothing else seems to exist. If you've ever tuned an old television to a dead channel, you've actually seen a tiny piece of the CMB without realizing it, that grainy static filling the screen. About 1% of it isn't just electronic noise, it's the faint whisper of the Big Bang's afterglow captured by your TV antenna. Scientists call this cosmic snow, and it's a humbling reminder that we're all bathed in the same ancient light, no matter where we are in the cosmos. What's astonishing is how perfectly uniform this background is. Point a microwave telescope at the emptiest patch of sky, you can find a region millions of light years across with no galaxies, no stars, not even wisps of gas, and you'll still detect the CMB's signature. It's like floating in the middle of the ocean and discovering the water stretches endlessly in every direction, no matter how far you swim. This omnipresence isn't just a curiosity. It's proof that the universe was once small enough for every point in space to be in contact, heated to the same temperature before expansion stretched it into the vast web we see today. But here's what's truly mind-bending. The CMB isn't just in space, it defines space. Every cubic centimeter of the universe, from the depths of intergalactic voids to the air in your living room, contains about 400 CMB photons. That means right now, as you watch this, trillions of these primordial particles are passing through your body, ghosts of a time before atoms, before stars, before planets even existed. They've been traveling unimpeded for 13 billion years, and you're their final destination. This all-pervasive nature makes the CMB the ultimate reference frame. Astronomers use it as a backdrop to measure everything from the motion of galaxy clusters to the universe's expansion rate. Even the Milky Way isn't stationary. We're moving relative to this microwave sea at over 600 kilometers per second, creating a slight, warm spot in the direction of our motion. It's like swimming through a river and feeling the current, except the river is the afterglow of creation itself. So the next time you glance at static on a screen or stare into the night sky, remember, you're not just looking at empty space. You're witnessing the universe's oldest light, a glow so pervasive it touches every corner of existence and connects us here and now to the very first moments of everything. Even the cosmic microwave background isn't completely still. It carries a subtle imp for decades. The cosmic microwave background wasn't just evidence for the Big Bang. It was the judge and jury settling one of cosmology's fiercest debates. Rival theories like the steady-state model argued the universe had no beginning or end, with matter continuously created to fill the gaps as space expanded. But the CMB, it didn't just favor the Big Bang, it dismantled the competition with forensic precision. The steady-state universe predicted no such microwave background. If space had always existed, there'd be no relic radiation from a fiery birth. Yet when Penzias and Wilson detected that uniform hiss in 1965, it wasn't just a curiosity, it was a death knell. The CMB's near-perfect blackbody spectrum, later confirmed by COBE, matched Big Bang predictions down to the tiniest detail. The steady-state model couldn't explain why the entire sky glowed with microwaves unless you twisted the theory beyond recognition. It was like finding a dinosaur bone in your backyard and insisting elephants always had scales. But the coup de grace came from the CMB's temperature fluctuations. Steady-state supporters scrambled to explain these tiny wrinkles, suggesting they might arise from local clumping of matter, but the patterns weren't random. They followed a precise mathematical rhythm, acoustic peaks in the power spectrum that only made sense if the universe had a hot, dense beginning. The steady-state model had no mechanism to produce these oscillations. It was as if someone handed you a symphony and asked you to believe it came from a room full of typewriters. Even more damning, the CMB's redshift. As the universe expands, light stretches, cooling the background radiation to just a few degrees above absolute zero. A steady-state universe with its perpetual creation of new matter couldn't account for this cooling. The numbers didn't just disagree, they clashed violently. By the 1970s, the evidence was overwhelming. The CMB wasn't just a clue, it was the smoking gun that made alternative cosmologies untenable. Yet the CMB didn't just disprove rival theories, it elevated the Big Bang from a controversial idea to the foundation of modern cosmology. Every new observation, from the precise ratios of hydrogen and helium to the large-scale structure of galaxies, fell into place like pieces of a jigsaw puzzle. The microwave background wasn't just one line of evidence, it was the Rosetta Stone that let scientists decode the universe's entire history. What's remarkable is how little wiggle room the CMB left. Competing theories couldn't just tweak their equations, they had to explain why the sky was bathed in microwaves with exactly 2.7 degrees of warmth, why those temperatures varied in specific patterns, and why those variations matched the distribution of galaxies today. It wasn't a matter of interpretation, it was checkmate. The steady-state model didn't fade away because scientists lost interest. It collapsed under the weight of data, crushed by the silent glow of microwaves that had been streaming through space since the dawn of time. Pinpointing the universe's exact age might sound like an impossible task after all. We're talking about measuring time itself from the very first tick. Yet hidden in the cosmic microwave background's intricate patterns is a cosmic clock, one so precise it's allowed scientists to nail down our universe's birthday to an astonishingly exact figure, 13.8 billion years. This number wasn't pulled from thin air. It's the result of painstaking analysis by missions like Planck, which mapped the CMB's subtle fluctuations with a resolution sharper than reading a stopwatch from across a football field. How does a faint microwave glow reveal time's grand scale? The secret lies in the CMB's acoustic peaks, those rhythmic ripples frozen in the light from when the universe was a seething plasma. Picture dropping two pebbles into a pond at the same time. The ripples collide, creating interference patterns. In the early cosmos, pressure waves from the plasma did something similar, leaving behind peaks and troughs in the CMB's temperature map. The spacing of these peaks acts like a ruler etched into the fabric of space. Measure them, and you're essentially reading the universe's expansion history. Planck's instruments were so sensitive they could detect temperature variations as small as 1 part in a million. This let scientists calculate not just how fast the universe is expanding today, the Hubble constant, but how that expansion has changed over billions of years. It's like replaying a video of an inflating balloon in reverse. Track the stretch marks precisely enough, and you can rewind to the exact moment the balloon was just a speck. Here's where it gets even more precise. The CMB doesn't just give us an age, it cross-checks it with other cosmic clues. The abundance of light elements like hydrogen and helium, the clustering of galaxies, even the behavior of distant supernovae, all independently point to the same 13.8 billion year timeline. It's as if the universe left multiple synchronized watches scattered across time, and they all tick in perfect agreement. What's remarkable is how much this number has refined over time. Early 20th century estimates pegged the universe at a mere 2 billion years old, younger than Earth. Later, Hubble's observations pushed it to 10 billion, then COBE and WMAP inched closer to today's consensus. But Planck's data, released in 2013, was the final nail, shrinking the margin of error to just 50 million years, a rounding error in cosmic terms. But why such confidence in this age? Because the CMB's patterns are a time capsule, encoding the universe's expansion rate at recombination. By combining this with measurements of dark energy's push and dark matter's pull, cosmologists reconstructed the cosmic growth curve like forensic accountants tracing every transaction back to day one. The math is so airtight that alternative ages now require inventing entirely new physics, something scientists don't do lightly. So when you hear 13.8 billion, remember, it's not an estimate. It's the universe's own testimony, whispered in microwaves, echoed by supernova, and etched into the very atoms around us. A number that wasn't guessed but uncovered, one frozen ripple at a time. The cosmic microwave background isn't just light, it's a shadow play cast by the universe's most elusive particles. Hidden in those subtle temperature ripples are fingerprints of neutrinos, nearly massless ghosts that flooded the early cosmos in such staggering numbers that they helped sculpt the very structure of reality. These weren't just background players, they were cosmic architects shaping the CMB's fluctuations in ways we're only now learning to decode. when the universe was a seething plasma of particles and radiation, neutrinos outnumbered protons and electrons by 1,000,000,000 to 1. Born in the first second after the Big Bang, these particles barely interacted with matter. 1,000,000,000,000 could pass through your body every second without a single collision. Yet despite their ghostly nature, they carried enough energy to influence how matter clumped together. Think of them like invisible hands gently kneading dough, subtly altering the density of the early universe before vanishing into the void. The CMB preserves their handiwork. As neutrinos streamed freely through the cosmos, their motion smoothed out small-scale fluctuations in the plasma, effectively erasing finer details in the temperature maps. The result, a distinct damping effect visible in the CMB's power spectrum, a telltale drop in the amplitude of fluctuations at smaller angular scales. It's as if someone took an eraser to the universe's blueprint, smudging the finer lines while leaving the broad strokes intact. Here's where it gets even wilder. By measuring this damping, scientists can estimate how many neutrinos existed in the early universe, and their calculations match predictions almost perfectly. The standard model of particle physics suggests 3 flavors of neutrinos: electron, muon, and tau. The CMB's fluctuations confirm this number with astonishing precision, leaving less than a 1% margin for error. It's as if the universe left us a receipt for its particle inventory, and neutrinos are itemized right there in the microwaves. But the real shock came when researchers realized these relic neutrinos weren't entirely massless. The CMB's patterns, combined with data from galaxy surveys, hinted that neutrinos must have at least a whisper of mass, enough to bend spacetime ever so slightly. We're talking fractions of an electronvolt, billions of times lighter than a proton, but enough to rewrite the rules. This discovery didn't just validate the CMB as a particle detector. It exposed a crack in the standard model, suggesting physics beyond our current understanding. What's breathtaking is how these ancient particles still surround us. The Big Bang's neutrino sea hasn't disappeared. It's cooled to just 1.9 Kelvin, permeating every cubic centimeter of space. Your body is being bombarded by them right now, relics from the universe's first second passing through you like shadows through a screen. The CMB doesn't just tell their story, it's the only reason we know they exist at all. Those faint temperature variations are more than cosmic static. They're the echoes of a neutrino wind that blew through the infant cosmos, leaving traces we're only now learning to read. And the implications are staggering. If neutrinos had been heavier or more abundant, the universe's large-scale structure might look entirely different: fewer galaxies, emptier voids. Their delicate influence proves how finely tuned the early cosmos was, balancing particles and forces with precision that still baffles physicists. The CMB isn't just a snapshot of light. It's a neutrino-scattered canvas, whispering secrets about the building blocks of reality that no telescope could ever see directly. One day, perhaps trillions of years from now, the universe's oldest light will vanish forever. Not because it stops shining, but because the cosmos itself will stretch it into oblivion. The cosmic microwave background, our most direct link to the Big Bang, is slowly but inevitably fading as space expands, its photons stretched thinner and thinner until they dissolve into undetectable radio silence. This isn't science fiction, it's the cold, calculated fate of a universe ruled by dark energy's relentless push. Right now, the CMB sits at 2.7 Kelvin, but that number is dropping by fractions of a degree every billion years. In another 10 billion years, it'll cool to half its current temperature. 100 billion years after that, barely a whisper above absolute zero. Eventually, the wavelengths of these photons will stretch so long that no telescope, no matter how advanced, could ever detect them. The afterglow of creation will have redshifted beyond the edge of the observable universe, like a ship disappearing over the horizon. This fade out isn't just a loss for future astronomers, it's the erasure of cosmic history. Without the CMB, civilizations born far in the future would have no obvious proof the Big Bang ever happened. They might gaze into the void and see only darkness, unaware that the universe had a fiery beginning. All the clues we take for granted, the uniform glow, the temperature fluctuations, the telltale patterns of acoustic peaks, will be gone, stretched into wavelengths longer than the universe itself. Dark energy seals this fate. As expansion accelerates, distant galaxies will vanish beyond an unreachable horizon, their light stretched past visibility. The CMB will follow suit, its photons diluted by an ever-growing ocean of spacetime. Future cosmologists might uncover indirect hints of the universe's birth, the ratios of light elements, the residual motions of galaxies, but they'll lack the smoking gun we have today. It's as if the universe is quietly closing its own history book, one redshifted photon at a time, yet there's a haunting beauty to this slow disappearance. The CMB's inevitable fade mirrors the universe's own trajectory toward cold, silent isolation. Stars will burn out, galaxies will drift apart, and eventually, even the last remnants of the Big Bang's glow will dissipate into the void. We're living in a privileged moment, a cosmic golden age when the afterglow is still bright enough to study, when the universe's origins are still written across the sky in microwaves. Future astronomers might envy us for the clues we take for granted, the ancient light we can still read like an open book. So when we study the CMB today, we're not just uncovering the past, we're preserving it. Every map, every measurement, every fluctuation catalogued is a snapshot of a window that won't stay open forever. The universe's first light is fleeting, and we're among the lucky few who get to witness it before it vanishes into the expanding dark. Among the cosmic microwave background's tapestry of near-perfect uniformity, there are a few oddities that refuse to fit the mold, none more puzzling than the so-called cold spot. Stretching across a patch of sky in the constellation Eridanus, this region is noticeably chillier than its surroundings, as if someone took a cosmic ice cube and pressed it against the fabric of space. At first glance, it might seem like a statistical fluke, but the odds of such an anomaly appearing by chance are less than 1 in 100. For scientists hunting evidence of parallel universes, this cold spot isn't just a curiosity, it's a potential window into the multiverse. The leading theory, this chilly aberration could be a bruise, a cosmic collision scar from where our universe may have bumped into another bubble universe in an eternally inflating multiverse. Picture a pot of boiling water with each bubble representing a separate universe. If two bubbles grazed each other during inflation, the energy released at the boundary could have left an imprint on our CMB, a kind of cosmic fingerprint. The cold spot's unusual temperature profile and lack of surrounding structure make it a prime candidate for such an event. It's as if we're staring at a dent in spacetime's hull, a relic of an encounter with another reality entirely. Not everyone's convinced, of course. Skeptics argue the cold spot could simply be a vast cosmic void, a region where matter is unusually sparse, stretching hundreds of millions of light-years across. As CMB photons pass through such a void, they lose energy due to the gravitational tug-of-war between entering and exiting, an effect called the integrated Sachs-Wolfe effect. But here's the catch. The void required to explain the cold spot would need to be so absurdly large that it defies typical models of cosmic structure formation. It'd be like finding a single crater on Earth wider than the Pacific Ocean possible, but wildly improbable. Then there's the polarization data. If the cold spot were truly a multiverse collision, it should leave a distinct swirl pattern in the CMB's polarized light, a signature of gravitational waves rippling from the impact. While tentative hints of such patterns have been spotted, they're not yet definitive. Future missions like LightBird or next-generation ground-based telescopes aim to scrutinize these regions with unprecedented precision, hunting for the telltale twists that could confirm a brush with another cosmos. What's thrilling is how high the stakes are. If the cold spot does trace back to a multiverse collision, It wouldn't just confirm that other universes exist, it would suggest they're close enough to touch, separated by a membrane thinner than we ever imagined. The implications would rewrite physics, philosophy, and our place in reality. Even if it turns out to be a void, the sheer scale of it would force us to rethink how structure forms in the universe. For now, the cold spot remains a tantalizing enigma, a Rorschach test for cosmologists. Some see a portal to alternate realities, others a challenge to conventional astrophysics. But one thing's certain, in the CMB's faint glow, even the weirdest anomalies aren't just noise. They're invitations to explore frontiers we've barely begun to map. Whether it's a cosmic bruise or a gaping void, the cold spot reminds us that the universe still holds mysteries bold enough to rewrite the rules. Deep within the cosmic microwave background's delicate patterns lies a cosmic curveball, an anomaly so perplexing that scientists half-jokingly dubbed it the axis of evil. This isn't some apocalyptic prophecy, but rather a bizarre alignment in the CMB's largest-scale fluctuations that defies conventional cosmology. Picture this: the universe is supposed to be isotropic, meaning it should look roughly the same in all directions. But when researchers analyzed the CMB's temperature variations across vast swaths of sky, they noticed something unsettling. The fluctuations weren't randomly scattered like confetti. They seemed subtly aligned along a particular axis, as if the universe had a hidden preferred direction. The name Axis of Evil emerged as a tongue-in-cheek reference to the way this anomaly seems to undermine one of cosmology's sacred principles, the Copernican idea that Earth holds no special place in the universe. If the cosmos has an axis, that implies a cosmic up and down, a notion that makes physicists deeply uncomfortable. The alignment isn't just slight, it's statistically significant enough that the odds of it happening by chance are less than 1 in 1,000. It's like rolling a die 100 times and getting only 6s technically possible, but wildly improbable. What makes this even stranger is how the axis correlates with other cosmic puzzles. The plane of our solar system aligns suspiciously close to this preferred direction, as does the mysterious dark flow, a baffling motion of galaxy clusters all rushing toward the same patch of sky. Coincidence, maybe, but in science, coincidences this glaring often hint at deeper truths waiting to be uncovered. Some theorists have proposed radical explanations, from the gravitational tug of a neighboring universe to pre-Big Bang imprints frozen into space-time. Others suggest it might be an artifact of incomplete data or observational bias, though repeated analyses keep confirming the anomaly's persistence. The implications are staggering. If the axis of evil proves real, not just a fluke or systematic error, it could force us to rewrite fundamental assumptions about cosmic inflation and the universe's symmetry. Standard models predict a featureless, random distribution of fluctuations, not this eerie large-scale order. It's as if we've spent decades studying a painting up close, only to step back and realize the brushstrokes form a hidden arrow pointing somewhere unexpected. Even the most cautious researchers admit this anomaly keeps them awake at night, wondering if we've missed a crucial chapter in the universe's origin story. Future missions may hold the key. More precise polarization measurements could reveal whether this axis leaves gravitational wave imprints, hinting at exotic physics beyond inflation. Or perhaps we'll find the culprit is something humbler, an unaccounted-for distortion from our own Milky Way's magnetic field. Either way, the axis of evil stands as a defiant reminder that the universe still guards its deepest secrets fiercely. In a field that prizes elegant symmetry, this awkward tilt in the cosmos' oldest light might be the clue that cracks everything open, or the glitch that proves even our best models are still laughably incomplete. Imagine space itself stretched like a rubber sheet. Would it curve like the surface of a globe, sag like a saddle, or lie perfectly flat? This isn't just abstract geometry. The shape of the universe dictates its ultimate fate, and the cosmic microwave background holds the answer. Those faint temperature fluctuations we've been exploring, they double as a cosmic carpenter's level, revealing space-time's curvature with precision that would make any craftsman envious. The verdict: the universe is flat to within a razor-thin 0.4% margin of error, a measurement so exact it's like confirming a bowling ball's smoothness down to the width of a single atom. This flatness isn't just a lucky guess. It's etched into the spacing of the CMB's acoustic peaks, those frozen sound waves from the early universe. In a curved cosmos, these peaks would appear distorted, like viewing a grid through a funhouse mirror. A positively curved universe would magnify distant fluctuations, while a negatively curved one would shrink them. But the CMB's peaks, they land exactly where flat geometry predicts, like a perfectly tuned piano where every note rings true. Missions like Planck mapped this with such fidelity that any significant curvature would have stood out like a misaligned brick in a flawless wall. What's mind-bending is what flatness implies. In Einstein's general relativity, spacetime's shape ties directly to its density. A flat universe means the total mass energy inside it is perfectly balanced against the expansion rate, a Goldilocks scenario called critical density. Too much matter and space would curve inward, eventually collapsing in a big crunch. Too little and it'd curve outward, stretching into eternal emptiness. Instead, we're riding the knife's edge with dark energy, dark matter, and ordinary matter combining in proportions that keep the cosmic books balanced to within a fraction of a percent. But flat doesn't necessarily mean infinite. While an infinite universe is one possibility, there's a wild card: topology. Imagine a flat sheet of paper rolled into a cylinder, locally flat but finite. The universe could, in theory, wrap around itself in similar ways. Some models suggest exotic shapes like a 3D torus, where traveling far enough in one direction would bring you back to your starting point. The CMB might hold clues here too. If the cosmos were finite, its wraparound geometry could create matching temperature patterns on opposite sides of the sky, like finding identical fingerprints on distant continents. So far, no such matches have emerged, but the search continues in increasingly precise data. The real shock is how perfectly flatness fits with inflation. That explosive expansion in the universe's first moments would have stretched spacetime so radically that any initial curvature became negligible, like blowing up a balloon to the size of Earth until its surface feels flat underfoot. The CMB doesn't just confirm this, it measures inflation's impact down to decimal places. Those 0.4% error bars, they're tight enough to rule out most alternative theories, leaving inflation as the only mechanism that explains such pristine flatness. Yet this precision raises haunting questions. Why is the universe balanced so exactly? If density deviated by even 1% in either direction, galaxies might never have formed. The CMB's flatness isn't just a fact, it's a fine-tuning puzzle that still keeps cosmologists up at night. Whether the answer lies in multiverse theories, deeper laws of physics, or sheer cosmic luck, one thing's clear. In the microwave sky's faint glow, we're reading the universe's architectural plans, drawn with geometry so perfect it borders on the surreal. The cosmic microwave background is more than a relic of light. It's a ledger of the unseen, a cosmic accounting system that tallies up the universe's hidden inventory. Among its most startling revelations, dark matter isn't just real. It's the scaffolding of reality itself, making up 27% of the universe's total mass energy. That's 5 times more than all the stars, planets, and gas we can see combined. And the CMB doesn't just hint at this invisible bulk, it measures it with the precision of a lab scale, using subtle twists in the ancient light's journey to weigh what our eyes can't perceive. Here's how it works. Dark matter doesn't emit or absorb light, but its gravitational pull bends spacetime like a hidden boulder in a stream. When CMB photons traveled through regions dense with dark matter, their paths warped slightly, distorting the temperature patterns we observe today. Think of it like looking through a frosted window. The glass blurs the view, but the pattern of distortion reveals the texture of the surface. By mapping these minute deflections, called gravitational lensing, scientists reconstruct where dark matter clumps lurk, even if they're completely invisible. The numbers are staggering. Planck's data pinned dark matter's contribution to 26.8% of the cosmic budget, a figure cross-checked by galaxy rotation curves and colliding galaxy clusters. But the CMB's real power lies in showing how dark matter shaped the cosmos. Those tiny temperature fluctuations we've discussed, they're not just fingerprints of early density variations, they're the playbook dark matter followed to build galaxies. Without its gravitational pull, ordinary matter, the stuff we're made of, would have spread too thinly, like flour failing to clump without water. The CMB captures the moment this partnership began, with dark matter's invisible hands already gathering the raw materials for everything to come. What's astonishing is how perfectly the pieces fit. The CMB's acoustic peaks, the spacing of those frozen sound waves, only align with observations if dark matter is cold, meaning its particles moved sluggishly in the early universe. Hot dark matter, like fast-moving neutrinos, would have smoothed out small-scale fluctuations, wiping away the seeds of galaxies. But the CMB's patterns demand a colder, heavier substance, one that pooled gently into gravitational wells, drawing ordinary matter along for the ride. It's as if the universe left us a recipe. For one cosmos, mix 5 parts dark matter to 1 part atoms, stirred gently over 13 billion years. The implications are profound. Without dark matter's 27% share, galaxies would be scattered randomly, their spins erratic, their clusters loose. The cosmic web, that intricate lattice of filaments and voids, wouldn't exist. The CMB doesn't just prove dark matter's existence, it shows us the blueprint it followed, a design etched into microwaves that we're only now decoding. And somewhere in those patterns, there might even be clues to dark matter's identity, whether it's WIMP, actions, or something stranger still, yet the mystery lingers. For all its gravitational influence, dark matter remains stubbornly invisible beyond its shadow. The CMB tells us it's there, how much there is, and even how it behaved, but not what it is. That's the next frontier. Future telescopes might spot dark matter's faint whispers in the CMB's polarization, or particle experiments could finally catch a single wisp of it in a lab. Until then, the microwave sky stands as our best evidence that most of the universe isn't just hidden, it's the hidden architect of everything we see. The cosmic microwave background surrounds us in every direction, bathing the universe in microwaves far too faint and stretched for human eyes to perceive. But with the right tools, we don't just detect this primordial glow, we transform it into vivid cosmic portraits, translating whispers from the dawn of time into rainbows of insight. Radio telescopes like the Atacama Cosmology Telescope or the now retired Planck satellite don't just listen to this ancient light. They paint it across the sky in false color maps, turning mathematical abstractions into landscapes we can explore. These images aren't snapshots in the traditional sense. The CMB's microwaves register at wavelengths around 2 millimeters, roughly 50 times longer than visible light. So researchers assign arbitrary colors to represent temperature variations our eyes could never see. Cooler regions might glow in deep blues and purples, while warmer patches flare in reds and yellows, creating thermal topographies of the infant universe. The result, a kind of cosmic ultrasound, where every hue shift marks a density fluctuation that would one day birth galaxies. It's as if we've developed night vision goggles for spacetime itself, revealing structures hidden in plain darkness. The process is equal parts art and science. Microwave detectors capture photons that have traveled for 13 billion years, measuring their energy with precision down to millionths of a degree. Supercomputers then stitch these readings into all sky maps, filtering out foreground interference from the Milky Way's dust and synchrotron radiation. What remains is the universe's skeleton, a blueprint of hot and cold spots untouched since atoms first formed. The colors may be artificial, but the patterns they unveil are as real as the ground beneath our feet. What's astonishing is how much these visualizations reveal. Without false color mapping, the CMB's temperature variations would be invisible gradients lost in a sea of microwaves. But by amplifying contrast and assigning hues, we spot the acoustic peaks, those frozen sound waves, as concentric ripples in the data. We trace gravitational lensing distortions where dark matter warps the light's path. Some teams even animate the maps, showing how different wavelength filters peel away layers of interference to isolate the primordial signal. It's cosmic archaeology, with every pixel a fragment of the universe's first moments. This translation of microwaves to images does more than aid research. It bridges the gap between data and human perception. When you gaze at a CMB map, you're not just seeing numbers, you're witnessing the afterglow of creation rendered in a language our minds can grasp. Those vibrant splotches aren't artistic license, they're guideposts to quantum fluctuations that became galaxy clusters, to gravitational wells that bent spacetime, to the very foundations of reality itself. The colors may be invented, but the story they tell is written in the oldest light there is, a story we're only beginning to decode. Centuries before we detected the cosmic microwave background, astronomers were haunted by a seemingly simple question: why is the night sky dark? In an infinite, eternal universe filled with stars, every line of sight should eventually hit a blazing sun, bathing the cosmos in perpetual daylight. This puzzle, known as Olbers' paradox, baffled thinkers from Kepler to Halley, until the CMB revealed a universe that's neither infinite nor static, but expanding and remarkably young. The paradox gets its teeth from a simple assumption: if space stretches endlessly in all directions, populated by countless stars, then no matter where you look, your gaze should eventually land on a star's surface. The collective glow would outshine the sun itself, turning the entire night sky into a blinding sheet of starlight. Yet when we peer upward, darkness dominates, sprinkled with mere pinpricks of light. The CMB cracks this riddle wide open by showing us two game-changing truths. First, the universe has a finite age. 13.8 billion years means light from stars beyond that horizon hasn't had time to reach us. Second, the extreme redshift of the CMB proves space itself is stretching, diluting starlight into invisibility before it can accumulate into a blazing sky. Think of it like standing in a forest where the trees are stars. If the forest goes on forever, every gap between nearby trees would eventually be filled by distant trunks, leaving no open sightlines. But if the forest is young enough that distant trees haven't grown visible yet, and if the spaces between them are stretching faster than saplings can sprout, then clear patches remain. The CMB is our proof that the cosmic forest is doing exactly that, expanding faster than light can fill the gaps, preserving pockets of darkness. Here's where redshift steps in. As the universe expands, starlight from distant galaxies gets stretched into longer, redder wavelengths, sapping its energy. By the time this light reaches us, it's often shifted entirely into the infrared or radio spectrum, invisible to human eyes. The CMB itself is the ultimate example: once visible light, now microwaves. This redshifting acts like a cosmic dimmer switch, ensuring that even if infinite stars exist, their combined glow never overwhelms the sky. But the knockout blow comes from time. The universe simply hasn't existed long enough for light from every corner to arrive. Imagine turning on a lamp in an impossibly vast room. Light needs time to illuminate distant walls. In cosmic terms, the walls of our observable universe lie 13.8 billion light-years away, marking the frontier of light that's had time to reach us. Beyond that, galaxies whose light is still en route, or regions expanding away so fast their photons will never catch up. The CMB's finite temperature, that fading 2.7 Kelvin whisper, is the thermal echo of this cutoff, proof that the cosmos had a beginning too recent to flood the sky with starlight. Olber's paradox once seemed like an argument against an infinite universe. The CMB reframed it as evidence for something even more profound: a cosmos with a fiery birth, a breakneck expansion, and a future where the darkness isn't just natural, it's inevitable. Those patches of black between stars, they're not empty. They're the universe's way of showing its age, its motion, and its ultimate limits, written in the absence of light we now understand was never meant to arrive. The Big Bang wasn't just a flash of light. It was an explosion of sound so cataclysmic it would have shattered eardrums across the cosmos. Yet today, the universe is eerily silent, a vacuum where no sound can travel. That's the paradox hidden in the cosmic microwave background. What began as a roar louder than a trillion supernovas has faded into a whisper we can only see, not hear. When the universe was a seething plasma of particles and radiation, it wasn't just hot, it was loud. Sound waves rippled through the dense, ionized gas at nearly 2/3 the speed of light, creating pressure fluctuations that would have registered around 200 decibels if there'd been air to carry them. To put that in perspective, a rocket launch hits 180 decibels at close range, enough to rupture human organs. The early universe's cacophony would have dwarfed that, a bass note so deep and powerful it vibrated space-time itself. The CMB preserves these sonic fingerprints, those temperature fluctuations we've mapped so meticulously. They're imprints of sound waves frozen mid-oscillation when atoms formed and light broke free. Scientists call them Barrian acoustic oscillations, a technical term for what's essentially the universe's first and last scream. A vibration so vast its wavelength stretched across hundreds of thousands of light years. The peaks in the CMB's power spectrum are like the grooves on a vinyl record, etching the rhythm of that primordial noise into the fabric of reality. Here's the twist: space today is silent because sound needs a medium to travel, and the cosmic vacuum is emptier than any lab-created void. But in the plasma-filled early universe, particles were packed so tightly that pressure waves could propagate with ease. The silent boom of the Big Bang isn't a contradiction, it's a reminder of how much the cosmos has thinned out. The same expansion that stretched the CMB's light into microwaves also diluted the once deafening roar into absolute silence. What's haunting is how close we've come to hearing it. If humans had existed during recombination, the sound intensity would have been lethal. Yet now, we're left reconstructing that violence mathematically, like archaeologists piecing together a shattered bell from its fragments. The CMB's temperature map is our sheet music, allowing us to simulate the universe's earliest sounds as eerie, rumbling drones. A soundtrack to creation no living being will ever experience firsthand. This auditory ghost story holds a deeper lesson. The universe's history isn't written only in light and matter, but in vibrations we're only learning to read. The CMB doesn't just show us the past, it lets us almost hear it, a roar frozen in time, waiting for us to decode its echoes. Deep within those tiny wrinkles of the cosmic microwave background lies one of the most astonishing ideas in physics: that the entire cosmic web of galaxies, stretching billions of light years across, owes its existence to subatomic tremors smaller than a proton. These minuscule quantum fluctuations, born in the first, incomprehensibly brief moment after the Big Bang, were stretched to unimaginable scales during inflation, becoming the gravitational seeds for everything we see today. It's as if the universe took the faintest whisper of uncertainty from the quantum realm and amplified it into a shout heard across billions of years. Picture this: in the vacuum of empty space, even at absolute zero, particles flicker in and out of existence due to quantum mechanics' inherent uncertainty. These fleeting disturbances are normally invisible, vanishing almost instantly. But in the universe's first trillionth of a second, during inflation's explosive expansion, space-time itself ballooned so rapidly that these quantum jitters got frozen into the fabric of reality. What began as fluctuations on the scale of 10 to the minus 35 meters, far smaller than an atom's nucleus, were stretched to cosmic proportions, spanning thousands of light years by the time inflation ended. The denser regions became gravitational wells where matter would later accumulate, while the emptier patches evolved into the vast voids between galaxies. The CMB's temperature variations are essentially a photograph of these amplified quantum ripples at 380,000 years old, warmer spots. Areas where those primordial overdensities compressed the plasma slightly, cooler spots, regions where space was stretched thinner. The fact that we can trace today's galaxy clusters back to these microscopic origins is nothing short of miraculous, like finding a mountain range and realizing its shape was determined by the vibration of a single atom billions of years earlier. What's breathtaking is how precisely this process matches prediction. Inflation theory not only explains the CMB's fluctuations but predicts their statistical distribution, the exact pattern of how frequently hot and cold spots of different sizes should appear. When Planck mapped these patterns, they matched the quantum hypothesis with staggering accuracy, down to fluctuations 1 part in 100,000. It's as if we uncovered the universe's DNA, with quantum mechanics writing the code and inflation magnifying it across the cosmos. Yet this raises a profound question. If quantum fluctuations shape the universe, does that mean reality is fundamentally probabilistic at its core? The distribution of galaxies, the location of superclusters, even the placement of Earth in a quiet galactic suburb, all might trace back to random quantum dice rolls in the first instant of time. The CMB doesn't just show us the aftermath. It's a window into a moment when the universe was so small that quantum uncertainty could shape its entire future. And here's the twist: without these fluctuations, the cosmos would be featureless. No stars, no planets, just a uniform, lukewarm soup of particles. The very existence of structure depends on those initial imperfections, those quantum defects stretched into cosmic scaffolding. In a way, we owe our existence to the universe's inability to be perfectly smooth, a flaw that became its greatest creative force. The CMB's wrinkles aren't just artifacts, they're the brushstrokes of quantum physics, painted across the sky on the largest canvas imaginable. Among the most profound revelations of the cosmic microwave background is how it whispers a fundamental truth about the universe's symmetry, a principle so deeply embedded in cosmology that it's easy to take for granted. The CMB's near-perfect uniformity, with temperature variations no greater than 1 part in 100,000, isn't just a curious fact. It's the bedrock of the cosmological principle, the idea that on the largest scales, the universe looks the same in every direction. No matter where you point a telescope, whether toward the Virgo supercluster or the emptiest void, the same statistical patterns of hot and cold spots emerge, as if the cosmos were woven from an invisible, consistent blueprint. This principle defies everyday intuition. Look around Earth and you'll see chaos: mountains, oceans, cities, a patchwork of unevenness. Zoom out to the solar system and planets orbit at wildly different distances. Even galaxies cluster unevenly, but scale up further to distances of hundreds of millions of light years, and something remarkable happens. The universe becomes smooth, like turning a jagged rock into fine sand. The CMB captures this transition with startling clarity. Its fluctuations are like grains of that sand, tiny, but distributed so evenly that no single region stands out as special. This isn't just a lucky coincidence, it's evidence that the universe has no center, no edge, and no preferred direction. The implications run deep. If the cosmological principle holds, it means Earth holds no privileged position in the cosmos, a humbling idea that traces back to Copernicus. When 16th century astronomers realized Earth wasn't the center of the solar system, it sparked a revolution. The CMB takes this further, suggesting we're not even at the center of the universe's structure. Those microwaves bathing the sky, they'd look almost identical from any other galaxy in the cosmos, a cosmic democracy where no viewpoint is special. Yet this uniformity posed a puzzle. How could regions of space too far apart to ever interact opposite sides of the observable universe share nearly identical temperatures? The answer, as we've seen, lies in inflation. That explosive early expansion ensured everything we now see was once crammed into a volume tiny enough to reach thermal equilibrium, like a cup of coffee cooling evenly before being flung across a room. The CMB's symmetry isn't just a feature, it's a fossilized moment when the entire observable universe could still exchange heat, preserving its harmony before inflation stretched it beyond recognition. But the cosmological principle isn't just about looking backward, it shapes how we interpret everything we observe. When astronomers measure the universe's expansion rate or map dark matter's distribution, they assume these properties hold universally, even in regions we can't see. The CMB justifies that faith. Its uniformity is the reason we can extrapolate laws of physics across billions of light years, trusting that hydrogen atoms in distant quasars behave like those in lab experiments. Without this principle, cosmology would collapse into chaos, with every direction telling a different story. There's poetry in this symmetry. The universe's oldest light doesn't just illuminate the past, it mirrors a deeper order, a cosmos where the largest structures echo the smallest quantum fluctuations. From the frantic randomness of the quantum realm to the vast, serene balance of the cosmic web, the CMB ties it all together, a reminder that even in the seeming chaos of creation, there's a hidden rhythm written in microwaves. Before the cosmic microwave background painted the sky with its telltale glow, the universe endured a kind of cosmic amnesia, an era so opaque that even light couldn't escape its tangled depths. Picture this, a time when the cosmos wasn't just dark, but impenetrably dark, a seething ocean of ionized gas so dense that photons barely traveled an inch before being swallowed and re-emitted by free electrons. This was the universe's dark age, a 380,000-year stretch where space itself was a blinding, featureless fog, hiding its earliest moments like a veil drawn over creation's first acts. What made this era so impenetrable was the violent dance between matter and radiation. In those first fiery millennia, temperatures were so extreme, hovering around several thousand Kelvin, that atoms couldn't hold together. Electrons, blasted free from nuclei by relentless photon collisions, turned the cosmos into a roiling plasma, thick enough to scatter light like headlights in a thunderstorm. If you'd been there and somehow survived, the entire universe would have glowed like the inside of a star, but with no stars yet born, just an endless, uniform brilliance with no shadows, no structure, no way to see beyond your immediate surroundings. This plasma wasn't just a barrier, it was a cosmic sensor erasing all traces of the universe's first moments. The incredible density meant any fluctuations or imprints from inflation, those quantum seeds that would later grow into galaxies, were smothered under the constant battering of photons. It's like trying to hear a whisper in a hurricane. The universe's earliest secrets were drowned out by the very energy that filled it. Only when expansion cooled the cosmos enough for electrons and protons to finally unite into neutral hydrogen atoms did the fog lift, releasing the CMB as the first unimpeded light. Yet this dark age holds tantalizing mysteries. Some theorists speculate that during this time, exotic particles or early black holes might have formed, leaving no trace in the CMB but potentially shaping the cosmos in ways we're only beginning to probe. Others wonder if gravitational waves from pre-recombination events might someday be detected, offering a backdoor glimpse into this hidden epoch. For now, it remains the universe's ultimate blackout period, a chapter written in plasma and erased by time, a reminder that even our oldest light carries echoes of an era we may never fully see. The cosmic microwave background does more than illuminate the past, it tells a story about who we are. That faint glow washing over Earth from every direction isn't just radiation. It's a bridge spanning 13.8 billion years, connecting every atom in our bodies to the universe's fiery dawn. When you look up at the night sky, you're not just seeing distant stars, you're immersed in the afterglow of creation itself, a participant in a narrative that began before time had meaning. This connection runs deeper than metaphor. The carbon in your cells, the iron in your blood, even the calcium in your bones were forged in stellar furnaces seeded by those tiny fluctuations in the CMB. The same quantum ripples that became galaxies also set in motion the chain of events that led to planets, oceans, and eventually life. We're not just observers of the cosmos, we're its literal offspring, shaped by forces so ancient they predate light itself. The humility in that realization is staggering. We're the universe's way of understanding its own origins, a fleeting thought in a conversation that began with a whisper of microwaves. What's equally profound is the perspective shift this ancient light offers. The CMB reminds us that Earth isn't the center of anything. From our vantage point, the universe appears to stretch equally in all directions, with no special location or privileged viewpoint. Those microwaves have traveled just as far to reach you as they have to reach a planet orbiting a star in the Andromeda galaxy or the edge of the observable universe. In a cosmos without edges or centers, we're simultaneously insignificant and extraordinary, a speck of dust with the ability to decode the sky's oldest secrets. Yet this isn't just a lesson in scale, it's an invitation to wonder. The fact that we can capture photons from the universe's infancy, map their subtle variations, and reconstruct events that occurred before Earth existed is nothing short of miraculous. Those microwaves were emitted before the first stars ignited, before the Milky Way took shape, even before atoms as we know them existed. And now, here we are, a species that evolved on a rocky planet around an unremarkable star, holding up antennas like cosmic seashells, listening to the echo of time's first tick. The CMB's ultimate message isn't written in equations or data points. It's written in the sheer improbability of our existence. Against cosmic odds, the universe arranged itself in a way that allowed galaxies to form, stars to ignite, and curious creatures to emerge who could trace their lineage back to a shimmering plasma. That glow is more than a relic, it's a mirror, showing us not just where the cosmos came from but our own place within it. Every time we study those microwaves, we're not just doing science. We're remembering where we began. From the static on an old television to Nobel Prize-winning revelations, the cosmic microwave background has rewritten our understanding of reality itself. This ancient glow isn't just a fossil, it's the foundation upon which modern cosmology stands, a Rosetta Stone that deciphers everything from the universe's explosive birth to its accelerating expansion. Every breakthrough confirming the Big Bang, exposing dark matter's grip, even hinting at parallel universes, traces back to those faint microwaves painting the sky. They've transformed wild theoretical guesses into precise measurements, turning cosmic mysteries into solved equations etched across 13.8 billion years. Yet the most thrilling chapter might still be unwritten. As new telescopes peer deeper into the CMB's polarization, as experiments hunt for primordial gravitational waves, we're on the verge of discoveries that could shatter current paradigms. Will we find proof of inflation's quantum origins, evidence of a multiverse, or something no theorist has even dreamed up? The CMB has been our guide this far, but its final lessons may be the most startling of all. So the next time you glance at the night sky, remember, you're not just looking at stars, you're seeing through a window lined with the oldest light in existence, a canvas where the universe inscribed its secrets before the first galaxies flickered to life. That glow connects us all to the dawn of time, and the next cosmic revelation might be hiding in its fading whisper, waiting for the right mind to decode it. If exploring these mysteries excites you, consider joining our community of space enthusiasts. Hit subscribe and let's keep unraveling the universe's greatest puzzles together, one photon at a time.